So acids and bases, does anyone know any examples? There's a lot of them in your day-to-day life. I'll give you a hint. Acids tend to be sour tasting. What do you think are some acids in your day-to-day life? Those are the ones you're probably more familiar with.
Lemon.
Sure, lemon, citrus, that's a great one. Let's think of an example for a base. Now, bases tend to be really bitter. Your parents may have done this to you if you were being a jerk when you were a kid. You may have been swearing, and they washed your mouth out. Never happened to you? No. Well, if you've ever tasted soap before, soap is extremely bitter. That may have happened to you in the shower. Soap is actually basic. It tastes very bitter as a result. So with acids and bases, you do have a lot of them in your household. Like if you've ever used vinegar on anything, vinegar is an acid, right? Lemon juice, any citrus. And on the other hand, you do have some bases, and most of the bases tend to be cleaners of some kind. Now, for our purposes in this class, we're going to say acids are something that when in solution, they will tend to lose a hydrogen ion. Okay, so they produce an H plus ion when you put them in solution. So for our purposes, that is an acid. Now keep in mind, this is not the only definition of an acid, but for grade 10, that is the one that we're going to use. Now, things like HCl, H2SO4, HNO3, H3PO4, these are all examples of acids. So if you ever see hydrogen bonded to any of your halogens, sulfur, or your anionic polyatomic ions, like nitrate, sulfate, phosphate, these are going to be acids. Now, I'm not going to expect you to know all of the acids, but by the end of today, I hope you'll have a good idea of some of the ones I might mention. By the way, the number of hydrogen ions, and the more readily they give up those hydrogen ions, the stronger that acid is. So, of these here, just knowing that, which one do you think is the strongest? Which of these acids do you think is the strongest? Which one has the most hydrogens to give? Yeah, phosphoric acid does. Phosphoric acid does. So, the strength of an acid we'll touch on a little bit more when we get to it there. But bases, on the other hand, these give up hydroxide ions. So when you put them in solution, they will dissociate and they will produce hydroxide. Now, similar to acids, the more hydroxide ions it produces and the more readily it does so, the stronger the base. So what do you think is stronger here? Sodium hydroxide or calcium hydroxide? They're both very strong bases, but calcium hydroxide has how many hydroxides per calcium? 2, right? So more hydroxides. Now, sodium hydroxide is probably the one cleaner in your house that's next to soap that you probably have under your kitchen sink. That is like Drano, drain cleaner, oven cleaner. Things like that are usually composed of sodium hydroxide. So common acids, things like citruses, carbonated beverages, vinegar, battery acid. These are all very common and probably all in your houses. And again, for citruses like lemon juice, orange juice, do you guys know what type of acid that is? I'm sure you've heard it before. Believe it or not, it's the same acid that they put on sour tasting candies. If you ever look at the back of a package of like Sour Patch Kids or something, on the package it'll tell you this type of acid is on them. Citric acid, right? Citrus fruit, citric acid. So that's the type of acid. Now, anybody know what type of acid vinegar is? By the way, vinegar and citric acid. Those are weaker acids. Anybody know what type of vinegar, what type of acid vinegar is? Have you guys ever heard of acetic acid? So that is vinegar. Vinegar is acetic acid. Bases are things like household cleaners, bleach, stomach antacids, soaps, baking powder. In fact, let's say I was working with really dangerous acid. Let's say I brought a jug of, 18 molar hydrochloric acid, which is really strong acid, and I was really angry here in a moment. I just doused some acid on him, which would be horrific, by the way. You would get crazy acid burns. But how do you think you would fix that? How do you think you would stop him from getting horrendous chemical burns? What would you do? What would you do? I'm going to give you a hint. Stomach antacids. What do you think that word means? Antacids. If you're having like acid reflux, right? Acid is coming into your esophagus, burning your esophagus. You may take one of these stomach antacids. You could drink, actually, some baking powder and water. That would work too. What do you think antacids do? Yeah?
Probably like the opposite of what an acid would do, or like just get rid of the acid.
Yeah, that's a good way of thinking about it. They neutralize the acid. So if let's say we had an accident and someone got some strong acid on them, baking powder is a good way to, neutralize that acid to stop them from getting chemical burns. If we made a big acid spill on the floor, that is something that I would probably use as well. I'd spread baking soda all over it. So this becomes very important in, anyone taking biology here, by the way? One person? I'm not sure if I'll pick on you then. Have you guys, how far are you in digestion yet?
Oh no, I'm taking it next.
Oh, you're taking it next semester, okay. Your body produces a lot of baking powder, sodium bicarbonate. Bicarbonate ions is how your stomach stops itself from getting burnt, in addition to a thick mucus layer. But it's also how that really strong acidic stomach juice, right? How that stomach juice kills pathogens. It helps break down denatured proteins. But you don't want it to burn your gut, your insides, right? You want to absorb those nutrients, and you don't want a thick layer of mucus in your intestines. So your body actually produces bicarbonate to neutralize that stomach acid. Now, acids have a sour taste. We're all familiar with their taste. In fact, culturally, most cultures have some sort of acidic food within them. This is very common when you ferment things, right? Acetic acid vinegar is the result of fermentation. There's lemon juice, lime juice. We love putting that on our foods. So we've acquired a taste for sour. But we've acquired a taste for sour over generations. Bases, on the other hand, they taste bitter. Right? Soap, baking soda, water. Another one here is beer, actually. Anyone here ever taste beer before? Their dad was being cruel, they gave him a sip of beer. How'd it taste? Did it taste good? No comment?
No comment.
What do you look at? Did you think it tasted disgusting?
It was okay.
It was okay?
Yeah.
Well, most people, their first reaction, most people, not everyone, most people, their first reaction is it's disgusting. It is the worst thing ever. The parents are cruel and they just want to see the kid's reaction. Now, that's because all bases are bitter, and in this case, hops, the thing they add to beer, is bitter as well. Now, bitter compounds tend to be acquired tastes. Most people don't like them the first time they have them. Why is that? Why would we have taste buds for bitter? Or for sour, for that matter? I'm going into biology a bit here, but from an evolutionary perspective. From an evolutionary perspective, it made sense to develop these tastes. So for acidic, that's a good sign that food is spoiled. right? We wanted to protect ourselves from spoiled food. Of course, we learned over many generations how to control the spoilage of food to our advantage, right? Fermenting foods, things like that. But bases in nature tend to be poisons. So most people, when they try something that has a bitter taste, they're like, ew, this is gross, get this away from me. And that's a natural reaction due to the fact that most poisonous substances are extremely bitter. So it was an evolutionary response to those poisonous compounds found in nature. Now, other properties. Well, acids and bases are conductors, right? We add an acid and base to water, it makes it conductive of electricity. Oh, by the way, if you had pure H2O, let's say you had pure water, is pure water conductive of electricity? It's actually not conductive. If you could have pure water, nothing dissolved in it whatsoever, it would not be conductive. It would be a complete insulator. Now, obviously, don't go jumping into your bathtub and throwing a blender in there. That's a horrible idea. Because even if you had pure water, the odds are there's going to be some dissolved solvent in there. Even just minute amounts will make it electrically conductive. And this is actually how I made that hydrogen balloon. Remember the day I blew up that balloon? Yeah, so I made that by mixing zinc with hydrochloric acid. Right, when I mixed zinc with hydrochloric acid, zinc plus HCl, my products were, I called this a single displacement reaction at the time, and it is a single displacement reaction. What would my products be here if this is single displacement? Zinc chloride and hydrogen gas. Again, don't forget about Hofbrinkel. So when you mix acids with metals, it will often produce hydrogen gas. Now carbonates and bicarbonates, when acids react with carbonates, bicarbonates, they produce carbon dioxide gas. Anyone here ever do the famous volcano experiment?
Who hasn't?
Well, apparently everyone except for you two hasn't. So the famous, I recommend you go, I'll bring some to our next class, and I'll show you the tragedy that took place to a small village. I know that sounds very obscure, but there's a good story that goes behind the production of carbon dioxide gas. But whenever you have baking soda and you mix vinegar with it, if you did the classic volcano experiment, you mix those two things together, you get this huge foamy mess by mixing those two things together, and that's the carbon dioxide gas that's being produced. Bases feel slippery, right? Soap makes your hands feel slippery. Soap dissolves a lot of those oils on your skin, which is why you get that slippery sensation. So bases will feel slippery. And then lastly, I want to talk about indicators today. I don't know if we're going to have enough time to do an indicator lab. So all you really need to know is indicators can tell you the pH of your substance to a certain degree. Indicators can tell you how acidic or how basic a substance is, but they're not going to tell you the exact value. The way they work is they will change colors at a specific pH. So you all have a pH scale in your booklets. Yours is filled in, correct? Or is it blank? No, it's filled in? All right. So pH stands for the power of hydrogen. Now you may have seen it written like this, the pH of something. It stands for power of hydrogen, and this is going to represent the hydrogen ion concentration in your solution. Now this is a very unintuitive scale, unfortunately. The reason I say that is because, do you think a pH of 14 or a pH of 0 has more hydrogen in it? Yeah, it's 0, right? Super stupid. This is a logarithmic scale as well. So you may want to write that in. This is a logarithmic scale. And I know I have some smart math people out there. Rhythmic scale. What does a logarithmic scale mean? I know there's some smart math peoples out there. So if I increase my pH from, 1 to 0, right? If I go from pH 1 to 0, how much stronger is this pH 0 solution than this pH of 1 solution? Is it 1 time stronger, 10 times stronger, 100 times stronger? It's 10 times stronger. So every pH value represents a change in hydrogen ion concentration of 10 times. By the way, those square brackets in chemistry means concentration, right? So if I ever write these square brackets here, this means concentration. Alright, so let's look at this scale now that we have some basic idea of what pH means. So pH is the amount of hydrogen ion in solution. And here we can see that the most acidic things on our scale is stomach acid. And stomach acid, by the way, is hydrochloric acid, that's HCl. And then we can see acidity here decreasing as we get to a pH of 7. So ant bites, some ants actually will spray acetic acid, or formic acid for that matter, which isn't as acidic as stomach acid. And then we have things like pure rainwater, which tends to be slightly acidic. You can get more acidic rain as well, depending on where you are. If you're around a smeltery or a refinery, places that process ores into metals, for example, they release a lot of sulfur dioxide gas. That could form sulfuric acid, and that sulfuric acid will cause the rain to be more acidic and can destroy trees and vegetation. Blood tends to be slightly basic, if ever so, and this pH right here is really important. What is a pH of 7? What is it written there? Neutral. So a pH of 7 is neither acidic nor basic. But all of these pHs below 7 are what? Acidic. All the pHs above 7 are basic. So the basic things are things like blood, seawater. You have detergents, so like your laundry detergents and soaps and stuff like that. And the most basic things under your sink are going to be like your drain cleaner and oven cleaner. You should wear gloves when you use those, by the way. Those are pretty much pure sodium hydroxide. Alright, so indicators. At a specific pH value, they will change colors. So, for example, phenolphthalein here is one of the most commonly used indicators. Slightly above pH. It's like almost a pH of 8, I want to say. It changes color from clear to pink. So if you have something, right, you have phenolphthalein in it, if it's pink, you know it's basic, right? It's got a pH above 8. If it's colorless, likely it is going to be neutral or slightly acidic. Or acidic for that matter. So these indicators, they don't tell you the exact pH value, But if you use multiple of them, they can zero in on what that pH is, right? Because all of these change colors at different pHs. But indicators are a nice way of just getting a basic idea of what pH your substance is. Lastly, I want to talk about this here. This is a neutralization reaction. I've already mentioned this once today. When you're talking about antacids, those tablets that can neutralize stomach acid, a neutralization reaction is what is occurring. Now, I had an insane professor that took extremely concentrated sodium hydroxide and extremely concentrated hydrochloric acid, NaOH and HCl, and he mixed them together in a beaker, and he let it sit there for a while, and then he drank it. Stupid idea. He could have been lying to us. It may not have been actually concentrated acid and base. But theoretically, what did he just drink? Theoretically, what did he just drink? Look. He mixed together concentrated HCl, concentrated NaOH of the same concentration, the same amount of each. What did he make? Yeah, he made salt water, right? He made salt water. So he drank some salt water. Obviously, you would never try this because if you screw it up ever so slightly, you're going to burn your insides. But he made salt water. So whenever you have an acid and a base and you mix them together, you are going to do a neutralization reaction where you're going to produce salt and water. Okay? Now, don't let your mind play tricks on you. Salt does not mean just NaCl. Any ionic compound produced by the neutralization of an acid and a base will give you a salt. So let's look at a couple more examples of this. And by the way, what type of reaction would you have called this before you learned it was called a neutralization reaction? It is one of the 5 types.
Double displacement.
Excellent, double displacement. Right, so this is a double displacement reaction. Calcium hydroxide. Is that a strong acid or a strong base? What is that one? That is a strong base. What about this one here? What's this one called? Yeah, that's actually sulfuric acid. And I'm not going to expect you to know how to name these things. Okay, I'm going to give you, on your test, I'm probably going to give you their proper acid name. In addition to, I will give you their way you've learned how to name them ionically. Because what would you have called this compound previous to today? Hydrogen sulfate, right? So on your test, I'm going to give you the proper acid name as well as the ionic name. So we have sulfuric acid, which is a very strong acid, and we have calcium hydroxide, a strong base. What are they going to produce? Neutralization reactions always produce 2 things. What are they? Yeah, you're going to produce a salt, and you're going to produce water. Okay, so think about it. Double displacement reaction. What is going to be my salt that I produce? Excellent. Calcium sulfate is going to be our salt that we produce, and we are going to produce water as well. So that is one important fact you do need to know. You need to know that a neutralization reaction produces salt and water. Okay, it produces salt and water. I'm going to also introduce you guys today to the concept of concentration, because when I brought that up a little earlier, you may have been confused by that. What makes an acid or a base dangerous? What makes an acid or a base dangerous? Now, when we do the lab next week on acids, bases, household chemicals, all of the acids and bases I give you, they're not going to be dangerous. They may be strong acids or strong bases, but they're not going to be dangerous. What makes them dangerous? So, an acid or base become more dangerous the stronger they are, right? And strength here is how readily they give up hydrogen ions and hydroxide ions. Right, how readily they produce hydrogen ions in the case of acids, or hydroxide ions in the case of bases. And how concentrated they are. And how concentrated they are. They become more dangerous the stronger they are and the more concentrated they become. Sorry, I worded that extremely poorly. And the more concentrated they become. What do you think concentrated means? What's your intuition about that? Concentration.
Like how much there is of it.
Yeah, good job. How much there is of it. Right? How much there is of it. Now, I could give you hydrochloric acid, stomach acid, which is really strong acid. But if I just put like a little tiny drop of it in a big pool of water, you're barely going to know that there's acid in that water, right? But then if I took vinegar, acetic acid, and if I concentrated it as much as you can before it crystallizes, we call that glacial acetic acid. Well, that acid could burn a hole through your jeans, right? We don't think of vinegar as being able to dissolve the cotton fibers of your jeans, but it can if it's strong enough, right? If it's concentrated enough. So again, the amount, that concentration, how much is in that solution per unit of volume, that can make that acid more dangerous as well, right? When we do labs here, we take a giant jug of 18 molar acid, for example. Molar is how we describe how concentrated. 18 is a lot. And we'll take that and we'll pour some in a beaker and then we'll dilute it with water until we get a concentration that's safe for students to use. Because if you guys use 18 molar and you got a drop on your skin, if you don't wash it immediately, you're going to get severe chemical burns. Right? So concentration is important. Concentration, you don't really need to know this. You'll talk all about this in grade 11. But to give you an idea, it's the amount of acid or base per unit of volume. Right, if you took the drain cleaner under your sink, right, the crystallized sodium hydroxide, and you put one crystal in a giant bathtub of water, right, that water is not going to be unsafe to you. But, you take one crystal and you put it in, a little tiny amount of water, well, now that's actually quite dangerous, right? That's going to be really concentrated. Does that make sense? Alright. So let's just do one more example of a neutralization reaction. This is more practice for you. And then I'll let you work. So, someone else give me a strong acid from your pages there. Just yell one out.
Nitric acid.
Nitric acid. Now, oh, by the way, the difference between a strong acid and a weak acid, I kind of indicated it within that example I gave. But a weak acid does not completely dissociate when you put it in water, right? So when I talk about like something like HCl, when we put that in water, it completely breaks up into hydrogen ions and chloride ions. You don't need to write this down. But a weak acid, something like acetic acid. Someone tell me the formula for acetic acid. First of all, what's the acetate ion if you look on your periodic tables?
C2H3O2.
I don't like it written that way. What's the other way it's written there? What's the other way it's written? It's also written another way in your periodic tables, no? Yeah. Yeah, I prefer if you write it like this. Now, instead of it being COO minus, we're just going to put an H on there. That's acetic acid. And the big difference here is when you put acetic acid in water, not all of it breaks up into acetate and hydrogen. So that's kind of the difference between strong and weak, right? When we throw acetic acid into the water, yeah, you got some that breaks up into your acetate ion. You have some that, and produces hydrogen. But you're still going to have some of that CH3COH, your acetic acid. Not all of it's going to dissociate into hydrogen and acetate. So that's the difference between strong and weak. And the same goes for bases as well. Now, lastly, let's do one more example. Let's say we had, you said nitric acid. Nitric acid is HNO3. Someone give me a base from their list.
Potassium hydroxide.
Sure, potassium hydroxide. This is a nice and easy one. What are my products going to be? Salt and water, excellent. And what is my salt going to be? Potassium nitrate. And what is my other product? Water. So again, you need to know absolutely that in a neutralization reaction you are going to produce salt and water.